So welcome everybody. It's good to see a nice collection of people online for this one. And this is a talk called Once Around the Cepheids. And the picture on the left is very representative of what a couple of Cepheid variables might look like. Very much the orange or yellow giant stars that we find in the skies, and quite a rarity in some ways. So the first discovery was 1784 when Edward Pigott noted the variability of a star in the constellation of Aquila the Eagle, the Eta star, that's this one here, and that it was changing its brightness by nearly a whole magnitude. And that was really the first discovery of variable stars. There's a couple of people joining now. Let's let them in. So the first discovery, 1784, of this variable star that changed its brightness, but didn't take long before several dozen variable stars had been identified, and a particular class of them were seen to all vary in a very similar way and were named the Cepheids, the Cepheid variables, named after the brightest of them, which was Delta Cephei, the fourth brightest star in the constellation of Cepheus the King, and a good one to choose because it was one of the most bright examples. And then really the fact that there was this grouping of them was picked up first by John Goodrich, 1784. He identified that of all the variable stars in the sky, the Cepheids were this particular class that shared a load of properties. And this is the Delta Cephei here, up near the pole. Here's Polaris, the pole star. Delta Cephei down here was the brightest of them, and this is it. Again, you can see that yellowy color to it. So quite a bright star and a yellow star, but particularly noted to be varying in a very curious manner. If you plot out the light curve of Delta Cephei over time, so we've got time running this way and brightness going up here, you can see this is half a magnitude, so it's changing by about one whole magnitude. So that's a factor of 2.5 in brightness because of the somewhat crazy way the magnitude scale works. You can see it has this characteristic slopes down and then sharply turns back up in brightness again, and then the ascent is very steep compared to the descent phase, and then again another sharp turn, and it repeats. It goes down slowly and up quickly. So rather a curious way for a star to behave. Another couple of people joining. Just letting those in. So we've got 24 now on stream live. And so this very curious behavior of these Cepheid variables with this characteristic light curve schematically shown at the bottom here shows how the brightness is varying in this sort of shark's fin sawtooth curve. You can see that in an image at the top here. There's a Cepheid variable right in the middle, fading and then quickly brightening again. So you can see the fade time. You can see the dates, April 28th, May the 4th, and so on. It's fading slowly and then it brightens very sharply again. And this pulsation is associated, we think, with the star changing its size. The size of the photosphere, the area from which the light comes, as we look at the star, the larger the area, the more light we are going to receive in direct proportion to the area, even if the temperature stays the same. Now, the next step in really understanding these Cepheid variables came with a study actually based on looking at the large and small Magellanic Clouds. This is a nice image of the two. They are dwarf galaxies that are the companions of the Milky Way galaxy in which we live. We don't get to see them from the northern hemisphere. They're only visible in the south. And the large Magellanic Cloud, this one, that's about 160, 170,000 light years away. And the small Magellanic Cloud about 220,000 light years away. But Cepheid variables are quite bright, and this lady, Henrietta Swan Leavitt, one of the heroes of astronomy, tracked down Cepheid variables in the large Magellanic Cloud and was able to produce a graph of the light curve of the individual Cepheid variables, many of them in the LMC here. And the trick to that, of course, is that the Large Magellanic Cloud is a long way away, and all the stars in it are essentially at the same distance from us, because they're all clustered together, all 168,000 light years away. And the size of the Large Magellanic Cloud is maybe a few tens of light years at most. So essentially, the distance to all of these Cepheids that she was able to measure within it is the same, to a fairly close margin. And that's very useful, because we can then say, well, the inverse square law of brightness versus distance can be ignored because their distance is a constant. And so any change in the brightness comparing one star against another must be due to its inherent power output, not because it's at a different distance, because they're all members of the Large Magellanic Cloud. And what she found was that she could get a very nice graph out of this, which she could plot a straight line through, which is always a good thing in any science. And what she discovered was that if she looked at the brightness of the stars on average, their average brightness during the period, or their peak brightness, it makes no difference. So the brightness is on this axis, and this is a true measure of their luminosity, remember, because they're all at the same distance, all 168,000 light years from us. If she drew a graph of their brightness against the period of their oscillation, then she found that they came out with a very nice straight line. Now, this is an amazing result. Why would you think that the period that they oscillated over would be related to their power output? Perhaps that's obvious. It's not obvious to me. But she spotted this, and it turns out that because of that, you can then look at a Cepheid variable somewhere else, and if you know its brightness and you as it appears, you can work out from this graph, based on the period that you see, what its actual luminosity is supposed to be. I'll explain that again. So if we measure the period and say it was oscillating on a 10-day period, then it must be at this point on the graph, and therefore have a luminosity of 12.8 on this scale. And we can compare that with the actual brightness observed, say for a Cepheid variable somewhere in the Milky Way, where we don't know the distance. But because we have the power output and the apparent brightness, we can compare the two, and by that standard candle law, the inverse square law of brightness versus distance, we can use it to get the distance of any other Cepheid variable wherever we can track one down. And this was a huge step forward for astronomy in terms of being able to measure the distance to different objects. So if we could see a Cepheid variable now in the small Magellanic Cloud, we'd only need to see one, and we'd be able to work out the distance and indeed the same was true for other galaxies much further away. Up to that point, the only way we had of measuring the distance to the stars was by the parallax method, which is to take two different viewpoints and see how the nearby object appears to shift its position against the much more distant background objects. You can do it with your two eyes. If you hold your thumb out in front of you against the screen with one eye open and obscure the star, and then swap eyes, you'll see that the object jumps, or that your thumb jumps relative to the background, and that's as illustrated here. And from that and a little bit of trigonometry, you can work out the how far away it is to the stars. So that was the only way that we had of doing that, and we would use the longest baseline we could arrange, which was the two ends of the Earth's orbit. So we would have a baseline, not the distance between your eyes, but around 300 million kilometers. And that would allow us to measure the distance out to really only the nearest stars to begin with, those that were within about 10 or 20 light years. Beyond that, we just didn't have enough of a change to be detectable with ground-based instruments. We've gone further using parallax by using satellites. The Hipparcos mission was measuring those angles involved down to 50 milliarc seconds, which is a truly tiny amount. It's like seeing the width of a human hair across the Atlantic. Phenomenal accuracy, and that took us out to a few hundred light years measuring the parallax. The idea was first suggested by another famous name in astronomy, Einar Hertzsprung, of the Hertzsprung-Russell diagram fame, and he attempted to take this parallax method and use it to measure the actual distance to some Cepheid variables, combining the result that Henrietta Swan-Leavitt had found of the standard candle inference from the period of a Cepheid variable. But if he actually knew the distance to one, then he could join up the distance scales between what we knew of parallax for the ones we'd been able to measure, and the next step, which is to then infer the distances of all observable Cepheids in the sky anywhere using that rule. Now, he failed. The Cepheids that he was able to find were too far away for his parallax measurements in 1913, but it was done later, and we managed to use the parallax to measure some that were within our range to get a decent answer, and that were indeed Cepheid variables. And that allowed us to calibrate the true distance to things like the Large Magellanic Cloud. And then this man came along, and with this very famous photograph of the Andromeda Nebula, as he called it at that point, the Andromeda Galaxy we would call it now. It's in the negative, so this is the bright nucleus of the galaxy and the spiral arms. But out here, he's labeled with a couple of marks a star, and you can see done a couple of others here and written N by them. N was for nova because they become brighter, but he's crossed out N and written var by it with an exclamation mark, because what he'd spotted was a Cepheid variable star pulsating away in the Andromeda Galaxy. And we didn't know whether the Andromeda Nebula, as he called it, was literally that, a nebula within the Milky Way, or a separate island universe, a separate galaxy in its own right, much further away and outside of the Milky Way. But by using the period of variability of this Cepheid variable in Andromeda and the distance ladder that had been established, and Henrietta Swan-Leavitt's rule for brightness versus period. He put all of that together and showed that this particular object was 1,000,000 light years away. And we knew at the time that no object within the Milky Way had been found to be more than about 50,000 light years from us. So this was clearly a separate galaxy, a separate object in its own right. And that really sealed a great debate about whether the Milky Way was the whole of the universe with everything in it, or whether there were these separate galaxies out there beyond. But he went a bit further and took some results from Vesto Schleifer, who had been measuring the speed of movement of galaxies in terms of their redshift, their Doppler shift, and used his Cepheid variable idea to discover more Cepheids in further galaxies, further away than Andromeda, and produce a plot, another straight line of the distance this way versus the speed of recession, the redshift in the Doppler shift of the spectrum of the galaxies that Schleifer had measured. He plotted the two against each other and got a relatively good straight line out of it, showing that the further away a galaxy was, the faster it was receding from us. And that was the real clincher proof of the expansion of the universe. The only real way that you can explain this idea that all galaxies are moving away and that they're all moving away more if they are already further away is to have the whole universe be expanding. Now, he wasn't the first to suggest the idea. That came a couple of years earlier by this chap, Georges Lemaitre, who was a Catholic priest and professor of physics, perhaps an unusual combination these days, but back then not so rare really. And he was a confidant and correspondent of Einstein's and had solved Einstein's field equations of general relativity and showed that they suggested that an expanding universe was very likely. And he did it 2 years before Hubble had produced the evidence to back it up. And so when that came along, the whole idea really became mainstream. And Lemaitre's idea was that if the universe was expanding, it must have been smaller in the past. And it all pointed back to an origin of what he called the primeval atom. Nowadays, we call that the Big Bang, the idea that everything emerged from a compact state. And so you can use this law now to use the redshift to find the distance of even more distant galaxies, even if you can't find a Cepheid in them. So we now have 3 rungs on our cosmic distance ladder. We use parallax first in our local neighborhood out to a few hundred light years and calibrate the distance of a number of known Cepheid variables within that. And then we use the Cepheid period versus brightness standard candle law to calibrate the distance to a number of galaxies, and then use that then gives us an indication of how the redshift varies with distance. And then beyond that, we can use redshift to measure the distance of all of the others that are further away. And on the right, we see Hubble's law, again, the speed-distance relationship, the redshift versus distance. And the fact that you can draw a straight line through it means that you can have h0, Hubble's constant, being the factor that relates distance to recession speed. Now, the expansion of the universe isn't a speed. We talk about the speed that galaxies are moving away from us and the fact that they are moving faster the further away they are. But really, this is an exponential expansion. And a better way of saying it is that there is 7% compound interest applied to the size of the universe per billion years. So it's a very, very low interest rate. The bank would probably charge you that for a year if you were borrowing unsecured loan. But we've borrowed the universe and we only have to see 7% inflation on it in a billion years. So it's really quite small. But there was a problem. And the problem was that when you started to measure that Hubble constant for different groups of Cepheid variables, we started to find that different people were coming out with different answers to it. Some were coming out with a number that's in the units they usually use was around 60, and some were coming out with a number around 80. And we would often lump it all together and call it 70 in the middle, but that really wasn't right. And if you did use 70, then you would find that the age of the universe would work out to be around 10 billion years. And that was a bit of a problem because some of the stars that we saw in nearby globular clusters appeared to be 12 billion years old. And they couldn't really be older than the universe, so it didn't make sense. And so during the 70s and 80s and into the 1990s, this was a bit of a problem until they realized with high resolution measurements that what was happening was that we were getting different groups within the Cepheid variables, two types. The classical Cepheids are younger and more massive stars, and the type 2 Cepheids are older stars, and they are from what we call population 2 as opposed to population 1. So the classic Cepheids are population 1. What does that mean? It means that they are formed recently out of the materials, the star forming materials that are present in the universe at the moment, which are quite heavily contaminated because they have a lot of what astronomers call metals, the elements heavier than helium, so carbon, iron, things like that, that are the result of several generations of stars living, forming the heavy elements, exploding, scattering them, and then being reformed into new stars. So population 1 are the most youthful and therefore formed out of the dirtiest material. Whereas the type 2 Cepheids are population 2. They're the middle age stars in terms of the universe, and they're fainter and have been around for a long time and were formed when the universe was a bit cleaner. And these two follow different light curve parameters. And it was the astronomer Bade that discovered this and really resolved the reason why we were getting two different values for the value of the Hubble constant. And it was because when we were looking a long way away, we were looking a long way back in time, inevitably. And so we were picking up mostly the one class of the stars, the stars had been formed early on in the universe and were therefore population 2, sort of metal-free stars, whereas the nearby galaxies, we're looking at the much more youthful stars that have been formed in a much dirtier environment. And so you can see them coloured in there, the two different classes, the population 1 and population 2 in the turquoise and yellow colours. I hope that comes through. And scattered around across the bottom are a number of confounding objects that were other types of variable star that had been misclassified as Cepheids just to make things more complicated. So once Bade had sorted this out, it meant that we could recalibrate things properly and know which class of Cepheid we were looking at. And it resulted in the doubling of our estimate of the distance out to Andromeda, out to, well, the modern figure is now about 2.5 million light years. And so we've got this now, this relationship that turns out not to be quite a straight line either, once we've really got to grips with it all. The period brightness relationship is for the two types of Cepheids, these two curves. It's just that if you're only looking at this group here, then it looks fairly like a straight line. It's only when you get to the very short periods and the very faint objects where the curve starts to kick in. So if we have a look at these classical Cepheids, then these younger stars, it turns out that they are yellow bright giant or supergiant stars, quite big, with masses 4 to 20 solar masses, and the spectral type, so the color really varies from an orange K type star up to a yellow white F type star. And of course the brightness is varying and the temperature is varying, so they're oscillating around, and you can't really pin them down to one particular spectral class. They're also very bright, being massive stars. The 20 solar mass monsters are up to 100,000 times as bright as the sun, and the period of oscillation is that of a few weeks. And as I said, these are young stars, and as with all massive stars live fast and die young. There are no old massive stars because their lifetime is too short. They burn through their fuel very quickly. And so these stars are on the giant branch of the Hertzsprung-Russell diagram. They've gone through the main sequence, burning their hydrogen to helium, and they're now burning in their cores to form heavier elements. The type 2 Cepheids turn out to be much fainter because they are low mass stars. They are stars around half the mass of our sun, and these are K-type stars, the orange color, and they last a very, very long time. They have a very long lifetime. Being so small, they burn their fuel very, very efficiently. And they tend to have therefore been formed a very long time ago in the metal poor population 2 time of the early universe. And they have lifetimes of hundreds of billions of years. So they're quite happy to outlive the current age of the universe several times over into the future. And these have periods of 1 to 50 days, and you can carve them up into several different groups, and it gets more complicated. So there are 1 to 4 days, 10 to 20 days, and longer ones. But if we had a look in our own galaxy, we'd find a whole group of Cepheid variables right in the center there, and that's enabled us to recalibrate the size of our galaxy as well. And we now know that the sun would be about here on this diagram, is indeed about 27,000 light years from the center. One of the brightest that we've discovered of these Cepheid variables is this one, RS Pupis, and this is a lovely photograph of it. You can see the very bright yellow colored star in the middle here, and there is this nebula that it's embedded in, which seems to have a number of rings of bright coloration around it. Those rings are light echoes, where the periodic brightening of the star sends the light straight towards us, but it also sends it in every other direction. And in particular, of course, it sends it sideways in the plane of the photograph, and then it collides with the gas and lights the gas up brighter. It's like a camera flash going off in the center periodically. But because the light has to travel sideways and then towards us, we see the direct camera flash from the direct line of sight, and then we see it bounce off different rings of material at different times because of the extended light travel time of going sideways first and then being reflected towards us. And these nebulae are sufficiently big that they're several light years across, that it makes quite a big difference to travel time. So we get these light echoes. So what is going on with these stars? What is the mechanism hiding behind all of this that's causing this pulsation that turns out to be so useful to us? I'll try and explain. It's called the Eddington cycle, and essentially it's like having a pressure cooker with a loosely fitting lid. You can start anywhere on this diagram. Let's start here where we've got the star at its brightest, at its largest size, putting out as the maximum amount of light. Because it's now putting out so much power, it loses energy faster than the core is feeding energy to it. And so the surface then begins to cool, and it shrinks down and shrinks back again to a smaller, denser state. And as it does so, the outer layers change in their transparency. So as it cools, you get an increase in the transparency and rapid heat loss, but then as it shrinks back down again, the increased density makes it more opaque. And what that does is bottles up the heat. So this is the lid of your pressure cooker slamming shut. And then the heat builds up inside the pressure cooker until it forces the lid off again, and then the heat can escape. And so it oscillates between these two states. So there is the system that's responsible for this is the partial and full ionization of helium. You have the energy generating core in the center where helium is being burned to form carbon, and overlying that we have a layer of helium at a temperature of 35,000 to 50,000 degrees, which is a fully ionized plasma. In other words, both the electrons have been ripped away from the helium atom by that energy of that temperature. And plasmas, fully ionized, they consist of the helium plus plus nucleus and a cloud of electrons flying around at high temperature. They're entirely composed of charged particles, and they are opaque to electromagnetic radiation. And so it acts as a light block for any electromagnetic waves trying to carry energy out from the core. And so it heats it up. It's effectively, the lid is shut. Now, further out in the star, towards the surface where it's cooler, we have a lower temperature, under 30,000, and that is such that one of the electrons gets recaptured. So you have a helium nucleus with one electron captured, so it's just helium plus as an ion. And that's a partially ionized gas now, and it's partially transparent. And so the orange outer layer can let light escape, but the inner yellow layer on the diagram is fully opaque to the light trying to carry heat from the core. And so what happens in that state is that the heat is trapped and the pressure increases and forces the star to expand outwards. And of course, as the gas and the plasma expands, that then leads to a cooling of the helium plus plus layer in its outer layers, and the star the helium ions recapture an electron, and it converts it to helium plus in that layer, and suddenly the layer becomes transparent, leading to all of that pent-up energy being able to escape the star. And so that transition from He2 plus to He plus opens the heat valve and lets the flash of light come out, and then the star starts cooling again, and shrinking back. And so it does this repeatedly over and over again. And so just to summarize, it goes back to the beginning again, and now the heat is going to result in, well, the increased pressure and the heat is going to result in the helium plus reionizing and becoming opaque and starting the whole process all over again. Now you can do some maths. We haven't got time for that. We'll skip over it. But what it results in is a constant that depends on the mass of the star as to how fast that energy is being generated in the core, and the amount of energy being generated in the core and the rate of power output drives that valve faster or slower, which is why you get that simple relationship between the period and the mass of the star, and therefore the overall brightness and period relationship. Now this is the Hertzsprung-Russell diagram, and we see the temperature or color of the stars, so hot O-type stars, cool red dwarfs and brown dwarfs down this end, and the brightness going up on the y-axis, and this line across the middle, this is the normal stars of the main sequence, like our sun, which is around about here on the diagram. And then we have the layers on top of that of the subgiants, the giants, the bright giants, the supergiants, and the hypergiant stars in further lines across the diagram. So where do we find the Cepheid variables? Well, they're along this strip here. And in fact, the two strips side by side represent the classic Cepheids, the larger, brighter ones, and the type 2 Cepheids here. If we look at that, zoom in on that so-called instability strip where the Cepheids live, we can explain what happens using a classic Cepheid, and we're going to choose a 5 solar mass star. So it forms up here, the sun would be down here, and it lives out its main sequence life, converting hydrogen to helium at this point, with a temperature of about 20,000 degrees and quite bright, until it runs out of its hydrogen in its core, and a reorganization that turns it into a red giant has to happen. It cools, the outer surface expands and cools, and it moves to the right on the diagram as the directly related to that drop in the outer surface temperature. It whizzes across the instability strip here and then settles down for a life as a red giant at this position, where it's very bright because it's very large, but it's at a sort of 4,000 degree temperature. In the core, we have the defunct leftovers, the helium that has been formed, and the hydrogen is now burning in a shell around it. And that shell continues to burn and powers the red giant star. But the helium core is constantly getting more helium dumped into it from that shell and gets bigger and bigger and more massive. And so eventually it reaches a point where the pressure and temperature in the core undergoes what's called the helium flash, where the helium itself ignites and starts to burn and form carbon. And so that causes a huge flash of energy, and the star changes from a red giant. It gains in brightness and gains in temperature rather, and comes over here and becomes a classic Cepheid variable. It changes in color from red to yellow, and so it's one of these yellow giant stars that you don't hear very much about. And it will stay as a Cepheid variable as long as that helium core is burning away inside the burning hydrogen shell and forming carbon. But of course, that can't last forever, and it doesn't last very long. In fact, it soon ends up building an inert, dead pile of carbon, as carbon ash left over from the process in that central core, and reorganizes itself again, crosses back this way, swells up even more, and becomes the next stage of red giant, where we have a dead core in the middle made of carbon with a helium shell burning outside it and an outer hydrogen shell. And in fact, if it was a heavier star, it would continue to do this, oscillating back over here when the carbon ignited in a carbon flash, and then building an oxygen neon dead core, which would take it back. And so it would zigzag from the type of red giant. Red giants all have an inner non-burning core of one element or another, and the Cepheids on the instability strip are where all the layers of the star are burning and there's no inactive core. And that's why they have a higher temperature given their mass, because they're using that mass more efficiently and using all of it to produce energy rather than having an inner lump of it in the center. And so large stars zigzag backwards and forwards across here until they get to the top, which is when they've built an iron core and they can't go any further and blow up as a supernova. But for a 5 solar mass star, it'll end up stopping at this stage, having formed carbon. It won't have the mass to go any higher, and then it will eventually puff off its outer layers as a planetary nebula and die that way. And so, to illustrate that, main sequence star here is burning hydrogen in its core. When it runs out of the ability to do that, you end up with a inner helium core with a hydrogen burning shell over it and an outer envelope of inactive hydrogen, making a red giant. But when the helium flash occurs, the helium ignites, so it's going from inactive to active, and the whole star is at a higher temperature because of it, and you've got your yellow giant Cepheid star where all the inner 2 layers are both burning, and then that will eventually build a carbon inactive core in the middle, and it goes back to being a less efficient configuration where it's not using all of the mass to produce energy, and so it reconfigures back to a type of red giant called an AGB star, an asymptotic giant branch star. Now, you also saw on that diagram at the bottom of the instability strip another class of star called the RR Lyra stars. These are also variables. They were recognized as being distinct and different from the classic Cepheids, or indeed from the type 2 Cepheids. And these have short periods, they're very faint, and they're, again, like the type 2 Cepheids, metal poor population 2 stars, often found in globular clusters. And talking of globular clusters, a lovely picture of one here with quite a few RR Lyra stars in it. Again, we can use these up to a point to do distance calibration. It's not as accurate as for Cepheids though. But what we can see when we look at the Hertzsprung-Russell diagram for a globular cluster is that all the stars in the globular cluster are the same age. And so what you find is a very interesting looking Hertzsprung-Russell diagram, because all the giant stars that would have been on the main sequence, that would have been here, have lived their lives and died and gone over to forming into the giant branch, and only the smaller stars that live longer are still on the main sequence. And in fact, there's a very neat turn-off point here where stars of a particular mass are turning off and progressing towards the becoming red giants. And from that turn-off point, you can age very precisely the cluster, because that would have been happening to begin with right up here on the diagram for the real monster stars. And like a fuse burning, it's burned all the way down to here in a certain time. So this ages the cluster for us nicely. And we can see that all the stars that were on here have now gone on. The most recent smaller stars that have ceased to burn hydrogen in their cores are on their way to being a red giant. Some of them are then, the older ones are red giants. And then a number more of them have gone over here to be yellow Cepheids. And then some of them are on their way back again to become AGB stars. And that's as far as it's got in its life. And so we can age the clusters and see like snapshots of the evolutionary history in different clusters by looking at the HR diagram of the clusters. And this is how you figure out exactly how the whole thing fits together. Now we do see one or two anomalies when we do that. We normally see this classic turn off, but sometimes we see some blue stragglers over here that are misbehaving and seem to be back on the main sequence and have been reignited. That's just a sort of confounding factor to the picture, and it's unclear as to what the origin of these blue stragglers is, but it may well be that they're in binary systems and that a star has been rejuvenated by being fed more pure hydrogen from the outer envelope of its neighboring star or something like that, and has gained a second lease of life. So that's probably what's causing that. And another complication to all of this is that some Cepheid variables, for reasons that I really don't understand, go into a harmonic mode of oscillation. Most of them behave with a nice simple one bass note, but some of them get into a double oscillation or even a triple oscillation, or sometimes combinations of those. And so the periods are shorter than they should be for the brightness, and this can confuse the distance estimation. So it needs to be very carefully analysed to make sure that the Cepheids are not in this multiple oscillation mode, because it's set to confuse you. And it's just like the vibrating strings on a guitar shown in this diagram here. So it's not quite as simple as it's made out. But nevertheless, going all the way back, just to summarise this, I think Henrietta Leavitt-Swan did a fantastic job of realising that if she studied these Cepheid variables all at one standard distance, she would be able to compare one against the other, and realised that the Large Magellanic Cloud gave her that standard distance of 168,000 light years. From that, she came up with the linear relationship between brightness and period, which we can now explain as this pressure cooker effect of the Eddington valve of the two states of helium in these yellow giant stars. But more than that, it enables us to bridge the gap between the distances we can get from parallax to the distances we can get from redshift. And without it, and without her work, we really wouldn't be able to tell how big the universe was or solve many of the problems of cosmology. And so it's amazing that these Cepheid variables, as a sort of freak of nature, are enabling us through very careful observation to put together the entire story of the history of the universe. And I shall stop there.
Bye.